Hello, can you hear me? Hello.
Yes, sir.
Yes,
Okay. Okay, these will be the topics for uh, today's class. Mostly, I'll be focusing on the drawbacks of Semaphore and monitors and its features. I don't think I'll be able to uh, complete in this class. So, before doing the talking about the drawbacks of Semaphore, let me discuss about some of the problems related to Semaphore, which generally appears in the different tests like gate exams and all. Okay, so we will have some idea of what we read and what questions are being asked. So there are a few of the problems that I have selected, and you can always look into other sources of such problems. So related to semaphore and as well as data access synchronization, that is using algorithmic approach. So if we consider the first uh, problem, so what will be the solution? The first one, this one. So it says that there are total five binary semaphores, M0 to M4, and there are five processes P0 to P4, and each process PI executes wait MI and wait MI plus 1 mod 4, and then it releases. So its wait means this is the P operation, this is, you can consider the V operation, the release. So this could cause thrashing, deadlock, starvation, but not deadlock, none of these above.
deadlock.
Which one will be the answer?
B, deadlock.
Because this is a pretty simple thing that we discussed in the last class also, that if you have got so it will end up into circular wait in case uh, because these processes are the philosopher, so it's equivalent to the Dunning philosopher problem. And the second one is also related to Dunning philosopher. What will be the solution for the second one? The solution to the Dunning philosopher's problem which avoids deadlock. So this one also we discussed earlier. So there are different ways to solve it, but this can be one option to ensure that uh, the condition for circular wait is um, avoided or is prevented rather. So what will be the option? What will be the correct answer here?
C.
C.
So to ensure that one particular philosopher picks up uh, the left fork before the right fork, and that all other philosophers picks up the right fork before the left fork. So just one of them, they should uh, pick up the forks in a different order than the rest of them. So this also we mentioned. So what about the answers for the next two? Give me the
Hello,
answer
sir.
for. Hello.
Sir, what is meant by thrashing?
Thrashing is high paging activity. Thrashing, I think it has been discussed in your memory management class, right? Thrashing, the term.
Yes,
You
sir,
should
it
have
has been discussed.
you should have encountered this term in memory management. What is thrashing? Anybody who knows the answer? I mean, in a simple term.
Sir, when there is not enough memory, but the program, the process needs them. So it acquires pages and releases pages, but the CPU cannot keep, the memory system cannot keep up with the CPU.
Hmm. So maybe this a simple example is you have got, so you know the degree of multiprogramming. I'm not getting who is answering asking the question, the names. So can you recall the degree of multiprogramming? The degree of multiprogramming means number of processes that are currently active in the system, right? So if you have got just one or two processes, so those two processes will be probably able to share the entire RAM. The majority of the RAM that is available for the user space, right? But if you increase it to 100, 200, 10,000, 20,000, so definitely if you are accommodating all the processes, so each and every process will expect a certain share of the RAM, and in other words, a certain number of page frames, because page frames are the physical space where the pages are accommodated in the RAM, right? So if you have got too many number of processes activated, or too many number of processes in the system, so the share in case of say uniform, or maybe, hello, hello, so the share that each process gets in such a case is very very small, right? So it may be just 2 frames or maybe 1 frame per process. So that's a very extreme case. Now you know that when a particular process is running, while running a particular instruction in that particular page which is in the frame, in its allocated frame, it refers to some other instruction which may be in some other page. If that happens, so then there will be a page fault, because this current page which is in the only frame allocated to the process will be need to be replaced, and probably some other page need to be loaded, say, if this is the case. Now again, when you are executing the instruction in that particular page, again there is a page fault because it refers to some other page. So it may happen because of very few number of frames are allocated to a particular process, and also because of the way it refers to other pages, like the page reference string also. So both might lead to uh, I mean frequent, very frequent page faults, and very frequent page faults is basically a thrashing, because in that case the CPU is more busy in performing the paging related activity, or to handle the page faults. Every time there's a page fault, there is a time wasted. So there is mostly it will be uh, page fault related activity rather than actual computation, and this is thrashing, which is quite unwanted. So if you increase the degree of multiprogramming, it increases the throughput, and then suddenly it falls when the thrashing sets in. Okay, so this thrashing is not probably a at all something related choice, but still it was just added as an option here. So what about the next two? What will be the answer for the next two questions?
So B.
8. 8.
It will be 8. So how do we get the value? So it was, you see the
10 minus
counting
6.
semaphore. Hmm.
There are
Yes.
4, like after 6 operations, I have 10 minus 6, 4. After
Hmm.
that, 4 V operations. So we have 4 plus 4, 8.
Yes. So it's a counting semaphore, means it's a general semaphore. So the value of the integer variable in that semaphore may take any number. So it is a non-zero value, but it can be 5, 10, 20, 30. There is no limit. So the semaphore only says that it should be a non-negative value, and it can, the minimum value can be 0. So now we know that in every p operation, if there is a wait, so what happens, it basically decrements the count. Okay, so decrements the count means you can think of that the value is decremented by 6 times, so 10 minus 1, and every time there is a v, there is an increment there that takes place, because in counting semaphores it is decremented and incremented. Okay, so 10 minus 6 for each p plus 4, it becomes 8. What about the last one, this last exam problem?
C3. C3.
Any other
Can
answer? Any other answer? Look into it carefully and then answer. What it says, that
None of
there are
these.
total, yes,
None of these.
what it says, you see, there are total, how many processes are there? Total 10 processes are there. Now 1 to 9, all the first 9 processes, they are executing the given this particular one, this p and v, uh, the critical section within p and v. That is what should be the case. And uh, I mean it can be something different also. So, but the p10, it is executing v mutex, then followed by I mean in place of p mutex, it has got a v mutex. So it may be that a v mutex, critical section, and v mutex, whatever. So what happens if one of the process out of the 10 executes a v mutex, then what it means?
Sir, it will
All the
increment. It will
Hmm?
increment and it will increment mutex, so another process can enter. if we execute P10.
So the thing is, you see, you consider a simple thing. Say the 9 processes, the 10th process was sitting idle. Say for example, it was not doing anything. It was not executing this state. So or maybe it has not been scheduled. So before that, all the 9 processes got scheduled. So each of the 9 processes, they will get stuck where it's p mutex, right? So p mutex, they will keep waiting. Although we say that one can say that what is the initial state of the this mutex. So if we assume that it is switched off, it is signaled off, then p mutex will ensure that all the processes 1 to 9 uh, are waiting in that p mutex, right? Now at that moment, if p10, which executes a v mutex instead of p mutex, then what happens? This v actually signals one of them, one of the waiting one. If that particular waiting process passes that p mutex test, it will enter into the critical section, and after executing the critical section for finite time, it will then execute what? What will be executed?
After critical section, it will execute v mutex.
V mutex. So the thing is, once the P10 executes a V mutex, it will signal some of the waiting. So out of 9 who are waiting, any of the process, and that process, once it passes the P mutex, it will successfully execute the critical section, and in turn it will execute the V mutex, the last statement also. Okay, once it succeeds, then what happens? That means it signals some other process which is waiting, and after that what it does? After that what it does? What is the code here? That particular process, what it does? It repeats. You see, it's a repeat forever. So it again goes back and goes for p mutex. So even if it waits, before it has executed p mutex, it has signaled some other process, right? So that process, in any case, it will enter into the critical section, it will execute v mutex. So what happens? Will any of these processes will be in the what is the largest number of processes that might be inside the critical section at any moment?
10 process, all processes can.
Yeah, it is possible, because whenever you are signaling one, the other one signals somebody, and so that process can execute and signal. So it may in turn like each and every process who are waiting will be signaled. That is that may be possible. And that means what is the largest number of processes? All the 10, and that option is not there. So this is none of this. Is that okay?
Yes, yes.
So it is repeat forever. So repeat forever means the process which succeeds to enter once because of the P10 signals other process and goes back to the P mutex, and this process goes on. What will be the answer for this one? Okay, let me bring the pen. I forgot to. So try to answer this. What is the answer? Hello. What will be the answer here?
A is no, because we have mutual exclusion, and for B it is true, we can have a deadlock.
We can have a deadlock. Okay, so that's the answer. So what it says, you see, there is a use of it has used 2 semaphores, S and T, right? So there are 2 semaphores, S and T, and you see the process A. Okay, let me see if it is working. Yes. So there is two semaphores, S and T. Now the process A, it waits for S, and process B waits for T. Now if both of them are set to false, or both of them are signaled off initially, that is not mentioned here. So what might happen, that it waits for S, it waits for T, and then after that it waits for T. So this down S is expecting some up S from process B. and that can only happen if the process B is able to execute this statement, and this is only possible if the process B is unblocked in this statement down T, and which this down can be made up by this process A, which is here up T. So this up T is here and this down this up S is here, and both are waiting for the other to go through and signal. So this is not possible. I mean, so both will be waiting for each other, right? So it says that let this execute up to this step and it will be signaling me, and then I'll go on and signal. So it's a circular kind of way in terms of the signal to be generated to the semaphore so that the other process can enter. Okay. What about this one? So these two uses two semaphores R and S. R is 0 and S equals to 1. So this has clearly mentioned the initial condition. It says that which of these statements are true. Operation A.1 cannot start until operation B.1 is complete. Let us think one by one. Operation A.1 cannot start until operation B.1 is complete. So to come to this point, it has to pass through this PR and PS, right? So PR and PS. So can it pass PR? Can it pass PR? What is the value of R here?
R is 0.
No, sir.
So R is
No.
basically signaled off initially. R is signaled off. So it expects that the process B should be executing what? V of R, right? And V of R is here.
Yes,
So
sir.
if V of R is here, so that means this A.1 cannot start until operation B.1 is complete. Is this true or false?
True, sir.
This is true. What about the second one? Operation A.1 and B.2 cannot execute simultaneously. A.1 and B.2 cannot execute simultaneously. Is there a possibility that they both execute simultaneously? Is it possible?
No, it can be possible because we don't have any problem with.
Yes, you see, say this operation B.1 does not depend on any condition here. It's not semaphore prior to that. So B.1 will be executed and automatically after that V can be signaled by this. And if this happens after that, if it gets preempted, so this A will not have to wait for PR because it has already been signaled and R is by the time 1. So it will skip this test. I mean, it will get this test true, and P of S AC is set to 1 initially. In any case, it will be skipping this. I mean, it will not have to wait, right? And after that, when it is executing A.1, maybe it gets preempted in this operation and B gets scheduled and B executes B.2. So A.1 and B.2 can be executed simultaneously. This is a false statement, right? What about the third option? I mean, the third, this operation A.1 and B.3 cannot execute simultaneously. A.1 and B.3, can they execute simultaneously?
No.
Can they be
It
executed?
is true, sir.
It is
It
true.
cannot, sir.
They cannot, because you see there is a V operation here. Say after these two getting simultaneously executed, there is a V operation. V operation means what? So V of S means this S value will be again set to 1, right? And this gets, so the point is A.1 and B.3, this and this. So until unless this VS gets executed, this B cannot execute this B.3, right? So this cannot happen that this A.1 and B.3 are executed simultaneously. So A.1 must be executed prior to B.3. Okay, so this is true. They cannot be executed simultaneously. This one. What about the last one? The D. Operation A.2 and B.3 cannot execute simultaneously.
They can, sir.
They can be.
Yes,
So
sir,
this
they
is
can.
also false, right? So they are basically two true statements. So there can be two true statements. What about the last this problem? What will be the answer? Initially S equals to 1 and T equals to 2. There are two semaphores here involved. The following operations occur. Which of the following is a possible state? See, it has been put into italics. What is the possible state of the system after these operations?
The system will not deadlock.
No, the options are given. We are not talking about deadlock. We are talking about who will be the processes, which processes will be blocked and which will be not blocked. They are simply talking about blocking. Which option will be true?
So he was talking about the fifth option in the first question.
The system. Okay. No. I'm asking about this one. Okay. This system maybe deadlock. So can there be a deadlock here?
No, sir.
No. So this is false. Okay. So yeah, this was also you have to say it's true or false. So I'm talking about the second. I mean this question now. Okay. Yes, the system will not be in deadlock. The option E. What about the next question? See, P executes down S. Down S means what? The value of S will be here. It will be 0, because down means it is already signaled flag is up, so it will put the flag down to make it 1, and it will not be unblocked, so there is no blocking. Now Q executes down T. Down T means the value of T will be 1, and this also will not block Q, right? Then Q executes down S. What is going to happen here? S is already 0. What will the value of what will be down S? Here Q will be blocked, right?
Wait, sir.
So it will be blocked. They are asking for whether it will be blocked or not. Then R executes down T. What is going to happen? T is set to 0, decremented further. There is no blocking because it was signaled. Still there is some free resource, and a down of T makes it 0, and R somehow escapes the blocking. And then R executes down S. Down S means what will be the
Again
fate of
blocked.
R?
Again
Blocked,
R,
sir.
R will be blocked because S is already it was 0 for Q also, so it will be blocked. Then up S by P. So P executes up S. That means S will be now 1, and it will be unblocking which one? So these two are blocked. So which one it should unblock?
Anyone, arbitrary.
It will
Arbitrary.
depend
R
who
or
will get the context.
hmm?
It will depend who will get the CPU first, like Q or R.
Yes. So generally we know if it is a strong semaphore, it follows FIFO, right? Because it is stored in a queue. So in that sense, it should be queue. But
Yes.
here, because you are talking about possibilities, you should not assume anything because it is not mentioned. So it may be either Q or R. And let's see which possibility clicks. Okay, then P executes down T. So up means P executes down T. So down T means T. So T value is 0. So who gets blocked here? Who gets blocked here?
P,
P.
sir.
So P gets blocked. So who gets definitely blocked? So P gets definitely blocked, right? So P gets blocked is written here, and P gets blocked is all the three possible. So this D option is not going to be true. But what is other? So either Q or R will be blocked along with P. So which option will be now true?
So C or D.
C, sir.
C or
C,
B.
sir.
See, it says that simply says that Q and R are not blocked. So this also will be false because
That
either
cannot be
of these
true,
two
sir.
must be blocked, right?
Yes.
And this is also true that all three processes cannot be blocked because one of the two will be unblocked, right? So this also is false. So which one is left now? The possibility, this C possibility is left. Got the point?
Yes, sir. Yes.
So you should not now if you assume it to be FIFO, this may not be true, but nothing is mentioned. So you should not assume that it is FIFO, because if it is FIFO, then P and P and R are blocked. Okay, but you cannot assume that because they are asking for. That's why the possibility is in italics, and you should be not considering that. And this is the only possible case. What about this one? So this 2020 is a year it appeared in the GATE examination. So this you can easily download from the internet also. What it says, there are n number of processes and there are two semaphores A and B initialized to 1 and 0. Assuming that the count is a shared variable initialized to 0 and is not used in the code section P. So count is initialized to 0. So there is no change in the value of count here or here in the P. Which one will be correct?
Sir, maybe all child means all the processes should exit simultaneously for that.
Which one?
But
Which option?
option I don't know, but there.
No, try to answer the in terms of the option and let me then
Okay.
find out the reason
Sir,
for that.
see,
Hmm?
sir. See,
Hmm?
it ensures that no process execute code section Q before every process has finished code section P. C.
It says that everybody should cross through this part so that uh, so there is a kind of borderline here. So everybody should pass through this point so that they can they will jump to this queue or they will be
Yes,
executing queue.
yes, sir,
So
something
even
like
if one process wants to execute, so no process proceeds beyond that. No process executes codes queue. So what about others? Do you agree with this option or there are some other answers? What is going to happen? Say we have got n number of processes. Now n can be anything. So let the first process enter. So P, now there is no so code section, there is no semaphore here, so it will be executed normally. And then it is wait A. Wait A, will it get stuck here? A is what? A is 1. So the first process will skip this wait. It will not have to wait here, right? It will skip this test without waiting because the signal was up. It will put it down and will come here and will increment count to count plus 1. Then what happens? So this count is the first process, the count is just 1. So where it goes? What is the next step for this process? The first process
signal, signal.
will be signal A. So signal A means maybe some other process, if it executed P, it will be waiting at wait A. Okay. So the first process, when it executes signal A, that means that first process is actually signaling the second process or some other process which is waiting here among the pool of processes. So it will basically pull this other process also and set and make it increment the value of count, right? So count will be 2 here. and after after it is 2, so the second process also will skip this, which will be false, and it will signal the third. So 1 2 3 4, each and every process will pass on through this, come here, and will signal the other process which is waiting. And how many processes will be pulled in this way, in this fashion? All the n minus 1 processes, you see, it will be pulled in this fashion. Now the nth process, so they will all be waiting where they will be waiting? In the B. This wait B, you see the value of B is set to 0. So they will be waiting here, right? It is wait B. So now what happens? So they are all waiting. So all the n minus 1 processes, they have crossed through this, and they will be, so they will skip this one, signal B, and they will be signaling A, pulling others. So you will be having all the n minus 1 processes waiting in this wait B, right? Now the nth process comes, and before the nth process comes, the n minus 1th process has already sent the signal. So this wait will be set to this value of A will be 1 here, right? So the nth processes will find it to be true. It will increment the value of count to n. Now this becomes true. This becomes true means this will now generate the signal B. So this signal B will release one process from here, and that process will be signaling the second process. The second process will signal the third process, like that, like that, like that. Okay. And once this happens, all these processes will be signaled, and they will be executing this code section Q. So it ensures that no process execute code section Q before every process has finished code section P. Is that fine? Is that okay?
Yes, sir.
Okay, so these are some of the problems. I think I'm not going through all of these. So these are again, okay, let us try this as the last one, and the rest you can try. I'll forward the slides. There are many such small examples or MCQs which you can try, and because the previous year GATE question papers are available, you will have a fair idea of what typical questions it may occur. I mean there may be. So these are simple ideas based on the P and V operations. What about this one? So this is not related to semaphores, right? This is related to shared variable access. So the concurrent processes P1, P2, P3, which access a shared variable D, and this then which has been initialized to 100. So D has been initialized to 100, and this is what they are doing with the value of D. The processes are executed on a uniprocessor system running in a time shared environment. If the minimum maximum values possible are x and y, what is the value of y minus x? First of all, let us find out what is the minimum value, what is the maximum value that is possible. If they all three execute simultaneously without any semaphore or anything, any synchronization primitive.
So minimum will be 50.
Okay, what will be the minimum value that is possible? Minimum value means minimum value can be through this decrement operation. So what might happen is this P2 reads the value of 100, and then it computes, makes it 50, but it doesn't commit. That means it doesn't write back. Okay, it holds. By the time it gets preempted, and P2 P3, they successfully increment the value of 100 to 120 and 120 to 130 maybe. Now P3 got scheduled, and it is just writing the value of 50, which it has computed earlier. So it is basically overwrite the values computed by P1 and P3, all the incremented values, and what will actually be retained at the end will be just merely 50, right? So the value of x will be 50, the minimum value. What will be the maximum value that is possible? The maximum means you should think of the incrementations. So the thing is, you can consider that this is done first, and it has sorry, I mean so this P1 and P2 reads the value. P1, P2 reads the value. So P2 writes also. So P2 writes 50, and then P1 writes. So both read the same value 100. P2 wrote it as 50, but P1 will overwrite 120 on it, right? And then P3 starts reading it. It reads 120, updates it to 130, and writes it back. So what value it will contain here? 130.
Yes,
Is that
sir.
Sir.
is that correct? What you got? Hello.
Yes, sir.
Yes, sir.
Yes,
Yes.
sir.
So what will be the value then? It will be
80.
80.
80, sir.
80. It will not be 50. It will be 80. Okay, so I think these are pretty simple. The rest, I think you can continue with this like this. And there are a few more examples. So the point is now we have talked a lot about data access synchronization using algorithmic approach, and you will find some there are some questions that is not using semaphores at all. They are just having like this one. So there are examples. So like these examples. So this is in 2015 gate exam. So this is purely on that the different attempts that we made, first attempt, second attempt, like that. So these are pretty simple in that sense, straightforward questions. Now this one you can see that this is somewhat related to the Lamport's bakery algorithm. Okay, the only thing is less than equal to, so it is not okay. Can you just tell me the answer for this, and so that I can switch to the other one. So this bakery solution, it's the small change that is made in the bakery solution. Okay, the answer is already shown here, so there's no point of asking the question anyway. So what it says, which of the following is true about the solution? So you see everything is perfect. So it sets ci to 1. That means there is a there is a lock, there is an unlock while it selects a token. Now there is a for loop checking for each and every process including itself, and if it is in a choosing state, in the jth process it waits till it is not choosing, and then this condition. What is the only change here is tj is less than equal to ti. If it is non-zero, it says that tj is less than equal to ti. If it is the case, it waits. So what is going to happen here? Can there be a deadlock?
No, sir. No. They cannot be there.
Can there be a deadlock here?
Hmm.
Think carefully and answer. Can there be a deadlock here? Say process 2 and process 3 are the only two processes which are interested. And process 2 and process 3, they have acquired. So can they acquire the same token value here? Can two processes still
Yes.
acquire the same token value?
They
Yes.
may,
They
sir.
can. Yes. They can.
Huh?
Yes, sir. They can.
Yes, it is possible, right? So 2 and 3 got the same token value, say 1. What is going to happen? Now this process 2, it
Yes,
says
but
that okay, 3 is not waiting, so 3 is non-zero. So this what it says, tj is less than equal to ti. So less than equal to ti. So okay, so this is true. So 3 waits for 2. And what about 2? Will 2 wait for 3?
Yes, sir. That will also.
Because the token value is same actually. So both waits, right?
Yes, sir.
So both waits for whom to pass. So 2 and 3 both waits because they got stuck with the same token value. So instead
Yes.
of breaking the tie, you basically forced the processes which have acquired the same token value to stop in a busy waiting phase. So will they ever be able to continue? Because
No.
they are the only processes which are, so the thing is, other processes will be waiting for them and they are waiting for each other to complete. So will it ever lead to a computational scenario? Will they ever be able to come to this step?
No. No, sir.
So this cannot cause deadlock is false. So this is possible. The progress condition is satisfied, is not satisfied. And the bounded wait condition is not satisfied. So the thing is, this at most one process can be in the critical section at end. So what it says that at most, so will it break the critical, the mutual exclusion property? Will it break the
No,
mutual
sir.
exclusion property? It
No,
will
sir.
not. So mutual exclusion is guaranteed. But what is not guaranteed is the deadlock situation. because if every process gets unique tokens, then the order is clear and they will follow the order. But if they somehow get the same token value, then they gets into a deadlock. That's all. And there is by no means they can enter simultaneously in the critical section. That is not possible, right? Okay, so in that way, we have talked about semaphores. We have talked about the different ways of using semaphores, the general semaphore and the binary semaphore. The topic that I think I'm not sure whether we have enough time to implementation of the semaphore using the test and set operation and or the swap operation. So we'll see if possible. I'll forward the slides on that. So now let us think of implementing the semaphore. Implementing means functions that will be used to write codes using semaphores. So semaphores are clubbed. So it's just like message queues, shared memory. They are also treated to be as a IPC mechanism, IPC primitive, inter-process communication primitive. And there are two variety of semaphores. One that uses the traditional system semaphores and another is a POSIX semaphores. And this, it has got its own set of functions, because we have already used the system v for creating shared memory. We know what it means. But for semaphores, we'll use a POSIX interface or the POSIX functions. And the POSIX has got two variants, named and unnamed. So can you guess what the difference between named and unnamed will be? So as it says in the named case, so it lacks any name or handle. So this is unnamed, I think. Missed it. So this is unnamed. So lacking any name or handle to locate them. Okay. So it says that if you have got say this is the parent process, this is the child process created from the parent. So if the parent has has created some shared memory, so using the same shared memory handle, the child also can access the same shared memory, right? So this can be one situation. So in this case, this shared memory, the space in the shared memory may be utilized to store the semaphore, because semaphore is also a shared memory, right? What we found. So this semaphore should be placed when you are trying to use a semaphore or several processes are willing to use a semaphore. So it should be hosted or it should be placed in some commonly accessible area, and this shared memory can be one such place. So whenever a parent creates a shared memory and it forks a child, so the child can also have the access to the shared memory without much hassle, right? And there we can create a shared memory associated with this, some portion of it. So, or it can be something like there is a parent thread, and this parent thread creates some other child threads. Okay, and we know that this P1, this C1 and C2, this is a parent thread, this child, these are the two child threads. So they all share by default some global variable, right? So when you are dealing with threads, they belong to the same process. So as here, these two are different processes, but here they are belonging to the same process say I, but here this is process J and this is process K. So in the same process I, you have got different threads, but all these threads, they have got access to the common globally shared global variable. Okay. So in this case, the semaphore will be placed in the global variable, in some global area or globally declared space. So the point is, you don't have to uniquely identify the semaphore by a different unique name in such cases. because by default, in this case, the threads, or in this case, two processes, they have got already something shared among themselves. So here the global variable or the heap, or here the shared memory accessible by multiple unrelated process may host the semaphore. The essential thing here is the code in the parent child or the threads already knows the address of the semaphore. So the way it is related, I mean, the processes are related, probably that decides which option we actually opt for. So unnamed semaphore is meant for those, and the named semaphore is meant for unrelated processes. So where this is, say, process, say, PRX, and this is, say, process PRY. Okay, and this PRY and PRZ are two completely different processes. They don't have any child parent relationship. They don't have they are not threads also. So this may be the producers, this may be the consumers. It may happen that this producer code has been written by some user 1, some programmer, and this code has been written by some other user, user 2. Okay, so because of that, they don't have anything that is shared. So for in such case, if they want to access some shared resource, say R, if they want to access it, they need to have some semaphore to enable access to it. So semaphore, say, S. So this S, because they don't have anything common, so this S should be declared as a named semaphore. Okay, where you should give the path. So the way we mention the files, the file name, path, permissions, and all. So that is the way. So the thing is, this is necessary for unrelated processes, and named semaphores gives them a path to the semaphore, and using that path you can always perform operations on it. Okay, so the point is, this named semaphore comes with a little extra baggage, because so some additional constructs are required. I mean, internally also they need to be maintained in different ways. So it comes with some extra baggage or extra overhead, and probably we don't opt for it if we know that we are going to have a semaphore accessed by multiple threads of a process, or in between the child and parent. So if it is these two cases, we basically opt for this kind of semaphore. If it is this case, we opt for named semaphore. But in both the cases, we have got more or less similar functions. So POSIX function interface for named semaphore, as you can see, these are the 3 header files to be added. These are pretty simple to use. So same open, it actually opens a semaphore which has not been created. If it has already been created, it will just attach this. So it will just return the address to that semaphore. So semaphore underscore T is a structure that keeps track of the semaphore which you are trying to attach, and the same open is the, so this same open, in that case we'll see in the example. So if this is PR, so the process X, and this is a process Y, so both the process X, process Y need to execute same open. Okay, like this. And this constant character name, so this name actually refers to like files, like the file names, you should have a semaphore name, and that should pass in the first argument. So both does the same thing. So the same file name, same name should be used in both of these. So you can use a macro to define the name. It was something like the shared memory. So int o flags, that should be set to o create. That means if you are in a creation mode, so if you would like to create, you should set it to o create, and it will be same for both o create. Okay, and the third is a mode, is the access permissions, whether you would have write access or only read access and all this. An unsigned value, this is the value that the semaphore will be initialized to. So that we know that every semaphore needs to be initialized. So it will be created and it will be initialized by the creator. So it can be either 0 or 1, or it can be any value n in case of a binary semaphore, in case of a general semaphore. So all in one step, you can basically create a semaphore and set its initial value. So what will happen if you have got same open in both the processes? What is going to happen? and if both execute the same open, what is going to happen? If px executes same open first prior, then it creates a semaphore, and if prx executes the same function with the same arguments here, it will find that the semaphore with that particular name already exists in the system, so there will be no more creation, rather it will just get the it will receive the address to that semaphore object, right? So that is how it is. So you just have to write it, and you don't have to care about who creates and who uses. So you can just write the same function with the same arguments here. Hopefully both will have the same kind of access in that, and the flags should be both create or create. There are other flags also, we just skip that, and you can set it to 0 or 1 as you wish. Okay, so it creates a new semaphore. If it does not exist or return a pointer if it does not exist, otherwise it returns a pointer to the existing semaphore. So rest of very simple. So same post, it is equivalent to the v operation of the semaphore. Okay, or the signal or the up, whatever you say. It is to release the, so it will be executed after it releases or when it is trying to release the resource. It returns 0 on success or -1 on error. Same wait, it provides a call equivalent to the p or wait or down. Okay, so for the p operation, if you have to p operation, you write same, you call same wait. If you have to call the v operation, you call same post. And same unlink is to remove the semaphore associated with the name. So if one is if one particular process unlinks it, same unlink, and if the other process tries to use it, then there will be error message. Okay, so you have to make sure that all the processes have used it and like that. So but same link can be placed in both of them. So same post, and so basically these are the 4 functions which are used to manipulate or use semaphores. POSIX named semaphore, and POSIX named semaphore is a very general one because you can use it for unrelated processes. If you wish, I mean, if you accept the overhead, you can use it for related processes or processes with having some hierarchy or even for threads, but that is unnecessary and we should not use it. And there are 2 variants of semaphore wait. It's same try wait. So this wait, instead of that, you can go for this or this version. So in this case, it is basically not going for a blocking kind of wait. If it finds that it is blocked, it will simply exit. I mean, it immediately returns. Okay, so it's try wait, and it is timed wait. Timed wait means it will mention how long you would like to wait. So I came to the phone booth, I'll not wait for more than 10 minutes. So I set an alarm, I sleep, but I sleep setting my own alarm in my mobile phone, say for example. So after 10 minutes, if nobody alerts me, if my turn doesn't come, I simply leave. That's all. And his try wait means I just come, if I find it's busy, I immediately leave. I don't wait at all. So apart from the waiting in a non-busy state, waiting in the buffer, getting suspended, apart from this option, you have got the other 2 options also in the implementation of the POSIX. And finally, you can also if you are willing, you can get the value. Okay, so initially you can get the value whether it is set or not or whatever, or getting the value, although these are not defined in the original semaphore definition, but you can always get the value. Getting the value means you can have an idea of the number of resource units that are available, but that does not mean that maybe after getting the value, before you make some change, somebody else would have utilized the value, so would have executed a post and have decremented the value. But this just gives you an idea that how many units are available, and if you want, you can get the value. So the first 4 statements are useful functions, but the rest of the 3 are also sometimes used. And in case of unnamed semaphore functions, you have got the same init instead of same open, and you have got same destroy instead of same unlink. So that's the only change. Okay, instead of same unlink, you have got same destroy to destroy it. So so this is for unnamed semaphore. So in the unnamed semaphore also, you can have the option to set this p shared. So this p shared, it's important. So this is the value that you set, it is 0 or 1. this is where you pass the pointer to the semaphore object. Okay, so instead of getting it returned, you basically pass it and receive the address of the semaphore that got created. This is a value that you set initially, and this is important, p shared. So p shared, if it has got a value 0, you should set the value 0 if you are using this unnamed semaphore between threads of a process. So if you are using the semaphore among the threads of a particular process, you should set the value 0. You should set p shared as non-zero if the semaphore is dealt by multiple processes, maybe parent, child, or whatever. Okay, so that is how we can make the changes. So when you are dealing with semaphores used by threads, you should set it's better to use unnamed semaphore, use same init instead of using named semaphore, and in that case set the value 0 here. And we'll have some examples of this in the book by Stevens, Matthew and Stevens. Okay, and the same destroy is just to destroy that semaphore. You can do it, and the rest of the operations will be the same. Rest of the operation means same post, same wait will be the same for both named and unnamed semaphores, POSIX semaphores. The two examples that, let me just talk about the examples. Okay, so can you see the screen?
Yes, sir. Yes, sir.
Yes, sir.
So here, so this is the first process. So what I did here, there are two processes. Okay, I think it's better to show it here itself, and I can execute it there. Can you see the screen?
Yes, sir.
So you see, we have defined, so we are talking about named semaphore. This example I have chosen, not unnamed semaphore. So this is a separate process and this is a separate process. They are written by different persons, so they don't, they are not related by any hierarchy or whatever. So we have given two names. This is one and this is one. I have just used same mutex 1 2. It can be just a1 a2 whatever. So these are semaphore names, and this is the pointer to the semaphore object, same underscore t, and same open we are calling same open semaphore name, the first semaphore, o create, in the create mode. This is a permission and this is the initial value 1. For the semaphore 2, the initial value is 0. So this second semaphore, o create. Okay, and within this 10 times this process is executing a p operation here on binary semaphore 1, then it says process 1 printing, and then there's a v operation on semaphore 2, you see. So you can say it's ps1 and this is v of s2 that they are doing. This is s1, say for example this is s2, and then after doing that it will remove, unlink the semaphores 1 and 2 both. So the other process just does something similar. So it has also specified the names of the both the semaphores, and that both of the processes should agree with the names, because they are after all trying to create a single shared resource. And this process also executes same open and same open like this, and with having the same arguments here, same initial setting. So no matter which one is executed first, either this one or this one, the initial state of the semaphores s1 s2 will be the same. S1 set to 0, s1 set to 1, and s2 set to 0. And if one of them has been if one of the processes already created this, the other process will just attach to it. I mean, it will get the pointer to that semaphore. So there will be no duplicate creation, and that the system will ensure, the operating system will ensure, because it is maintaining such semaphore resources and it is available. One can see it in a specific path in the system. So we will find that those objects are created, the semaphore objects are created, which is basically a shared resource. Like the shared memory, such resources are created for the time being. Now this also does the same thing 10 times. It will make a p operation on s2 here, and after doing the same printing, but it says process 2, it executes v of s1. So what it does, v of s2, it actually signals to this process, and v of s1 actually signals to this process. So if we execute and both, then unlinks this one. So if we execute these two processes simultaneously, what do we expect? What do we expect the output? So this is say s2 and this is say s1. There are two semaphores. Okay, so in two doors, there are two semaphores, two bulbs you can think of. Now process p1, so this is process p1 and this is process p2. So p1, if this is glowing, then process p1 enters. When it leaves, it switches on this one. Okay, so it's something like this, on to this, and this actually switches on this while it leaves, before it leaves. So what will be the output of this? If the initial condition is s1 equals to 0 and s2 equals to s1 is 1 and s2 0.
The process 1 printing, process 2 printing.
But how many times? 10 times each. So the thing is, process 1, process 2. Can process 1 print consecutively 2 times?
No, sir, no.
It will be strictly alternating. The way we have placed the semaphores, it will be strictly alternating. So although we have placed semaphores, we try to enforce that they should be continuing in the strictly alternating fashion. So S1 is done, and after PS1, only then VS2 will be actually signaled. So this is not a good example of the use of semaphores, but it shows that how you can use semaphores. And this I have intentionally written to show that you can have more than one semaphores, and they can be shared, and one can signal. So the P and V may not be in the same place. P of S1 is here and V of S1 is here, and vice versa. So that is what the objective is. So if I look into the execution, now let me execute the code. So this is the process 1 and this is the process 2. So if we execute it, this semaphore 1, the process 1 gets compiled. Its name will be proc1, and process 2, its name will be proc2. So if we execute process 1, what is done here? The change that I made, what is the change that I made? So although I have used here, so same 1, same 2, it was not the same example here. So it was same 1, same 2. Here I make, and here I make same 1, same 2, same 1, right? The just now the example that I have shown. Is that fine? The process 2, it executes P of S2 and V of S1, and process 1 is executes P of S1 and V of S2. So this is the example that I discussed right now. So let me try this one. So this one, now you see. So process 1, after, see, earlier it kept on printing. So now process 1, after printing process 1 printing 0, it waited. Now where it is waiting? It is waiting in the P of S1 and expecting the process 2 to signal it. Now once I run the process 2, it will get the signal, and each one will signal the other, right? So they are alternatively printing it. And there's a small sleep added, sleep of 1 second. That's why it's taking some time. Is that fine? Now if I make both as same 1 1, so if I simply ignore the second semaphore that is present here, then what is going to happen?
They will not wait for it.
So the thing is, so definitely I cannot run both of them simultaneously, right? So if I run process P1 before I start running process P2, doesn't matter because it just says that. So now the situation is, you have got a single door, entry door, and you have got a single semaphore, same one. And process 1 and process 2 both are just same processes, similar processes, just to some other person wrote it, that's all. So both, if any of them, we will see it on, it will enter, access it, and it will signal it. And if the process 1 is executed fast and we take some time to execute process 2, then before it starts, it exits and enters multiple times, right? Now when I start executing process 2 also, now it becomes alternating. Why? Because when the process 1 was executing, process 2 is waiting in the sitting area. So whenever it signals process 2. But whenever process 2 has entered, now the process 1 again comes back in the iteration and it waits. So it's now strictly alternating. And as you can see here, the last 5 are only process 2, because by the time the process 1 has ended. So this is a better way of writing it, because if both processes are eager to enter, that should be strictly alternating. There should not be any biases. But if one of them is ready, so it can enter any number of times without being bothered about what the other processes are doing. So although I have shown that there are 2 semaphores, in this case it's better we use one semaphore, because both the processes are basically doing the same thing. They are entering into the writing area or printing area and then printing something, displaying something. Is that okay?
Sir, here we were lucky to have alternating now.
No, alternating does not mean that it should alternate. I mean, it may happen that because of some scheduling issues, process P or process 1 is preferred more because of priorities or whatever. So process P1 prints twice and then process 2, then again twice and process 2. Anything can happen. But yeah, this is by chance you can say it's alternating. So if they are having the same priorities, everything same, so it should be alternating. That is the kind of fairness that you expect, and this is happening here.
Oh.
But we cannot guarantee that it will be alternating. So to guarantee that it is alternating, we should be doing that. I mean, that's the case. Okay, so this will be the last slide. So this is the drawbacks of semaphores. What are the drawbacks of semaphore? Semaphore is a signaling mechanism, as we found with so many examples and scenarios. But the unfortunate thing is, there is no guarantee or control of the proper usage. The processes using semaphore must be aware of each other and coordinate accordingly. Now, if I am writing the producer code and if you are writing the consumer code, so I am the user one, I wrote it perfectly okay, but in the consumer code you made some bug. So instead of V of say mutex C, you forgot to place it in proper place. So that might create problem for me also. So the thing is, if they are not written in a proper way, so a bug in this particular process, which might have been written by some other person, some other programmer, might affect my performance and my my performance. I might starve or get into a deadlock situation because of some bugs set by you. So that's a big problem. So the improper usage of semaphore may lead to starvation or even deadlocks. So semaphore does not guarantee that there will be no deadlock. It is up to you. Semaphore is just a construct. You are given the ability to control shared access and to make it starvation and deadlock free. But how you do it, it's up to you. It's entirely the responsibility lies on the designer of the solution and the programmer of the solution. Simply in case of the dining philosopher, it appeared to be very simple, and we wrote it and we found that it ended up in a deadlock situation. So whether the code is reliable enough and it should work properly, it depends on the designer's understanding his skill, and also how it's not only the designer, but when you try to write this code like this, a very large a very complex software might be involved with multiple semaphores, some general, some binaries, and that there might be some bugs, design bugs, or maybe programming bugs. And if this happens, the most unfortunate thing is you wrote a code today, an application which involves semaphores, and you tested it thoroughly. You never encountered the error that the mutual exclusion is violated or the starvation is a problem. Might be after 3-4 years there is some situation and it triggered that bug. I mean the bug is now evident in a typical situation. So the thing is, such bugs might be occurring once after maybe 2-3 years. Now once you found the bug, you know it was a deadlock situation, you roll back and all, then you try to find out what is the bug, what the bug was. You ran it once again, you didn't find anything wrong in it. So fixing the bugs involving semaphores maybe uh, maybe tricky. I mean, it may not be always, because you have to go through the design and find out the design fault. So dealing with semaphores, although the solution seems to be very elegant, but dealing with semaphores, the designer or the whoever designs the solution, you have to entirely rely on that person's understanding and his efficiency, because we also found that it is not easy to, you can visualize it using a layout or mapping it to some classical problems, but this is obviously challenging. So the solution is we should rely on the compiler, and the compiler should take some responsibility, and that is what is provided by the monitor construct. So we'll see it in the next class, how the use of the monitor helps us to get rid of I mean to facilitate uh, getting some solutions. Okay, so that is the end of the semaphores.